a tangent line or a tangent line approximation of a function centered at a point. This is the point where the tangent line intersects the curve. We'll call it C. C is an abbreviation for center, because it's kind of the center of this approximation. It's a linear function because it's a tangent line with the same value and the same first derivative as your function at that point. And occasionally, as you continue to take classes, especially Calculus 2, we use a lowercase p with a little subscript 1 to denote this function, because since it's a line is a polynomial of degree 1. And this notation would only become important like in Calculus 2, because in Calculus 2, we will also talk about like second degree polynomials that approximate my function and third degree polynomials that approximate my function. And so we would use different subscripts to tell me what degree of approximation I'm using. But for today, and for Calculus 1, we're just going to use first degree polynomials. So we'll use little p1 to represent my tangent line. And exercise 1 just says, give the formula for the tangent line approximation of f centered at C. So I know that my line could be written in the slope-intercept form of a line. And I want my slope of my tangent line approximation to be equal to the slope of my function at the point x equals c. So of course that's the derivative of the function. And then I also need these to intersect each other at that point. So they need to have the same value. So I could write something like p1 of x is equal to f prime of c times x plus b, and I need this to be equal to f of c. I want them to have the same value at this point when x is equal to c. And that means I'll replace the x with a c, and then to solve for b, I've got to subtract f prime of c times c from both sides. And so my tangent line approximation is going to be f prime of c times x plus b and maybe a better way to write this is like this, where I'm going to factor out the f prime of c part. That's a more common way to see this written. So you don't have to derive it fresh every time, but if I were to ever ask you to give the formula for the tangent line approximation, what's the tangent line approximation? It's this. So p1 is a function of x. X only appears once here because it's a line. But it depends on what, the value of the function is, because I want it to have the same value of the function when x is equal to c. When x is equal to c, then I get c minus c, and that's 0. So the first term is 0, and I only get f of c. And it also has the same slope. because the derivative of f is the slope of f. And I'm evaluating that at c. So we've seen this before. I mean, you remember this from like section 1.5, but again, just to keep it fresh in our mind and do some scaffolding, let's do one of these problems too. I do not want to. Ugh. Okay. Find the tangent line approximation of the function f of x equals e to the power x at the point x equals 0. And so that means I could write something like this. That's our formula for the tangent line approximation. And since I know f of x is e to the x, what is f prime of x? E to the x. That's nice. I'm going to need f of c, where this time c is equal to 0, the center of my approximation, the point where my tangent line intersects my curve is supposed to be the point x equals 0. So we'll call that c. And let me ask you, what is f of 0? 1. Yeah, e to the power 0 is 1. And this time it's pretty easy. The derivative, f prime of 0, is also 1. And so I'm ready to write my tangent line approximation. Because f prime of 0 is 1 times x minus, we'll see as 0, plus f of 0 is 1. So this is super easy. This is just x plus 1. And, you know, a lot of things canceled really fast when we had e to the x as my function and c equals 0 as the point. But even if things didn't all cancel, you know, you still use the same formula. And then let's graph it to make sure it works. We got e to the x, my function, and then we've got x plus 1, my tangent line. And yeah, what I want to point out to you right now is that, yeah, the tangent line has the same value of my function at that point, right? They intersect at the point x equals 0. It has the same slope as my function, and because it has the same value and the same slope, that means if I zoom in really close, there's kind of a particular neighborhood around x equals 0 over which the blue line is a good approximation of the red curve. And it wouldn't really matter whether you used really the red function or the blue function to evaluate a point near x equals 0, because it would be pretty close to the same. That's not true everywhere, right? Like if you zoom out over here, then now the blue line is a really bad approximation of the red curve. But at least within some small neighborhood, it's pretty close. And that's the idea of approximations. So this is the reason why we care about this today specifically. What if I want to find a solution to a nonlinear equation like cosine of x equals square root of x? Okay? There is no easy way to find a value of x so that cosine of x is equal to square root of x. I mean, I could square both sides and get like cosine squared of x equals x, but still, it's not easy to find a value x that's equal to cosine squared of x, right? There's not an analytic way to solve this with pencil and paper. So again, what do you do, because this happens all the time in real life, that you have equations that are nonlinear, that you can't solve with pencil and paper? Here's what we would do. We would rewrite the equation so that one side is 0. For us, that means you subtract square root x from both sides. The other side of the function, or sorry, I should say the other side of the equation, on the left side of the equation, we're going to name that function f. So f of x is equal to cosine of x minus square root of x. Now, if I can find the zeros of this function, that would be the solutions to the original equation. So that means here's my x-axis, here's my y-axis that has values of my function. If I can find a place where I have a zero of this function, then that value of x would be the solution to my equation. Okay. Step 1, choose any x value inside the domain of this function and name it x with a little subscript 0. X subscript 0 is what we call the initial iterate. Step number 2, we're going to find a tangent line approximation of my function centered at x0. Okay? Step number 3, we're going to solve a linear equation instead. Even though I can't solve the nonlinear equation, because it's really tough, I can always solve a linear equation. Solving linear equations is super easy. You've been doing it since 8th or 9th grade. So we can solve a linear equation. And what that linear equation looks like is whenever I set the linear tangent line approximation equal to 0. And the logic here is that, like, I know that tangent line approximation isn't actually my function, but remember it was pretty close to my function within kind of a small neighborhood. So let's pretend it's the same thing as my function. And if I'm close enough to a 0 of my function, then solving this equation should get me even closer. Okay? So let me set the line equal to 0. And you remember P1 of x was really just f prime of c times x minus c plus f of c. And that's what we're setting equal to 0. And so whenever I said, oh man, it's really easy to solve a linear equation, this time I'm trying to solve for x. It's because it is. Let's subtract f of c from both sides. And on the left side, we still have f prime of c times x minus c. And then, if I want to solve for x, let me divide both sides by f prime of c. And then the last thing I need to do, if I want to solve for x, is I need to add c to both sides. So what I just wrote down, I'll put a little box around it. This is a formula for finding a 0 not of f, but for finding a 0 of the tangent line approximation. A 0 of P1. And what I have to do is take the place where I'm centering my tangent line approximation, take f of c, divide by f prime of c, and then take c minus whatever that ratio is, and that will give me a 0, the place where my tangent line approximation crosses the x-axis. Now, step 4 is saying, let's update the center of my tangent line approximation to be this 0 that we just found a moment ago. And when I update the center of my tangent line approximation, go back to step 2, find the tangent line. Step 3, solve the linear equation. Step 4, repeat it again. Update where the center of that tangent line approximation is going to be, and repeat this process over and over and over. Okay? So step 4 is what puts this all together into what we call an iterative method, because step 4 is saying, take this, but don't just do this one time. Do this as many times as it takes to get a good approximation of the 0 of my function. So look closely at the subscripts. We're going to start off with an initial iterate where k is equal to 0 to start off with. That's the initial iterate. And you get to choose that one. Well, probably on a test, I'll give you the initial iterate because I want your work to look the same as mine. So on a test, I'll give you the initial iterate. In practice, if you're an engineer, you choose the initial iterate where k is equal to 0. And then if I want to solve for x with a subscript 1, I'm going to use this formula because k plus 1 would be 0 plus 1, and so that's x1 is equal to this function of x0. And what we're going to end up with, after I repeat this process a whole bunch of times, is a sequence where I have my initial iterate, and then I calculate this formula one time, and I get my first iterate, and then I do the formula a second time, and I get my second iterate, and then I do the formula a third time, and I get my third iterate, and I can make this sequence as long as I want, continuing to produce additional iterates from this formula. And the hope is everybody sits around and crosses their fingers, and we really, really hope that this sequence of numbers is getting closer and closer to the true 0 of my f function. And if I find a 0 of that f function, like we talked about before, finding a 0 of this f function means I've solved my equation that I was trying to start with. So this is how you solve equations in practice if you can't actually sit down and solve them with pencil and paper. You can get your calculator out and do this iterative technique over and over and over again, and you get an approximation that's close enough in the end. Okay, does that make sense? So this particular iterative method is called Newton's method. And this is something that you need to memorize for sure for your next test, because we'll need to use it to solve an equation on your test coming up Thursday. This is not the only iterative method. If you're curious about other iterative methods and how calculators work in general, you can take a class here called Numerical Analysis. It's like an upper level math elective, junior, seniors take it, but it's a really, really cool class. And so this is just a tiny little introduction to numerical analysis in a way. And exercise 4 says, use Newton's method to find a solution of cosine of x equals square root of x, starting at, and this is my initial iterate that I'm supposed to use, x0 equals 0. So let me show you how to do that. We're going to define my function f to be cosine of x minus square root of x. That way, if I find a 0 of f, I solved my equation. Then what is f prime of x?
Sine x.
Mm-hmm. Negative sine of x.
Yes. 1/2 x to the negative 1/2.
Yes. So then the power rule, this remember is x to the 1/2 power. So it's minus 1/2 x to the power negative 1/2. And the first little bullet point says we're going to solve this by hand. So let's solve this by hand first. Obviously, on a test, you're not going to be able to use Excel. So we're going to have to solve it by hand. This might be the most important part. And to solve it by hand, we need to make a table. The leftmost column of my table is going to be x. And then, or sorry, k. It's a k, not an x. It's going to be k. And then the next column is going to be labeled x sub k. And then the next thing is going to be f of x sub k. And the next column is going to be f prime of x sub k. And then the last column is going to be f of x k divided by f prime of xk. And that should be good enough for our solving by hand problem. We have a 5-column table here. And the reason I want to make this table is because if I write this out really neatly, and I can read my own handwriting, and this is going to break it down step by step so I don't make any silly mistakes on my way to finding the solution. And so when k is equal to 0, x with subscript 0 is supposed to be 0. That's given to me in my problem statement, what my initial iterate should be. Then I need to find what is f of 0. Well, f of 0 would be cosine of 0, and you could just put this in your calculator. You don't even have to really think about it. Just cosine of 0 minus the square root of 0, which should be 1 minus 0, so that's 1. And then f prime of x would now be f prime of 0 for this row of the table. And so I do negative sine of 0 minus 0.5 times 0 raised to the power negative 0.5. And that is, oops. That's interesting because it's like divide by 0 error when you have 0 raised to a negative power. Let me graph this really quick because I'm interested in seeing what this looks like. Cosine minus square root. Let's see how that goes. Okay, I see what's the issue. Okay. So this was a bad choice of initial iterate. Whenever I said start at x0 equals 0, that's not a good choice for initial iterate because in order to use Newton's method, I have to calculate the derivative at x0. But does everybody see what the problem is? Why I'm stopping here? Because if I have 0 to the negative half power, that's the same thing as 1 divided by the square root of 0. But I can't divide by 0, right? I can't do 1 divided by 0. So I can't actually start there. And that means we've got to choose a new initial iterate to start from, not x0 equals 0. That was never going to work. So let's choose something else. This time, let's say we start from x0 is equal to 1. And we just start all over again. And now we got to calculate f of 1. Cosine of 1 minus the square root of 1. And make sure your calculator is in radians. That's another important thing. Anytime we're using a trig function in this class, and I don't say otherwise, then you have to use radians in your calculator. So hit the DRG button and just verify that radians has the underline, and then pick that out. And then cosine of 1 minus 1 in radians should be negative 0.4597. And whenever we're doing this Newton's method stuff, we're going to use the same numbers over and over and over again in calculation. And so your round off error is going to compound on itself. Every time you round, you're introducing a little bit of error into the calculation. And if you keep using this number to calculate that number, to calculate that number, to calculate that number, then it's going to build up. So for these Newton method problems, I want you to go ahead and report your answer with 4 significant figures, like here. Normally, for your answers on a test, 3 significant figures would be enough. But since we want a little bit of extra precision, let's use 4 significant figures. And if you want to use 5 or 6, then be my guest. But 4 is what I'm going to do. So now I need f prime of 1, which is going to be negative sine of 1 minus 0.5 times 1 to the negative half power. And that should be minus 1.341 when rounded to 4 significant figures. Okay, and now we got to divide those numbers. So type in negative 0.4597 divided by negative 1.341. And we get 0.3428. And then you restart. For the next row of the table, k is equal to 1. To calculate x with a subscript 1, what should I do?
Wait, how do you get the k? Where does the k come from?
The k goes up by 1 every time.
Okay.
This table is going to end up with a bunch of rows. And we're just going to number them off 0, 1, 2, 3, and 4, 5, 6, and so on. Okay? So right now I'm looking at the second row of the table and I'm wondering, what is x with a subscript 1? What goes right here in the second column?
Would it be the value just solved for?
Nope.
0.3428?
No. We have to use the Newton's method formula, right? We're going to take the previous iterate minus that ratio. And so the previous iterate is 1. I need 1 minus 0.3428. Now I have to evaluate my function again at 0.6572. So I'm going to do cosine of 0.6572 minus the square root of 0.6572. And I will get negative 0.01897. And now I have to evaluate the derivative of my function at x equals 0.6572. And so I'm taking negative sine of 0.6572 minus 1/2 times 0.6572 raised to the power negative half. And I'm going to get the number negative 1.228. And then now I divide those numbers. So negative 0.01897 divided by negative 1.228 is positive 0.01545. And how do I find, on the next row of my table, when k is equal to 2, how do I find this number right here, the x subscript 2? Yes, exactly. Yeah, to go to the next row of my table, I need to use the Newton's method formula, which says take the previous iterate minus that ratio. So I'm taking 0.6572 minus 0.01545. And I will get 0.6418. And now I've got to take the value of my function at 0.6418. So take cosine of 0.6418 minus square root of 0.6418. And I get negative 0.0001047. And then I take the derivative here. So take negative sine of 0.6418 minus 1/2 times 0.6418 raised to the power negative half. And you will get negative 1.223. And then divide those two numbers, so 0.0001047 divided by 1.223. And I get 0.0008561. And then to get x with a subscript 3, I take 0.6418 minus 0.0008561, and I get 0.6417. On your test, I'm going to tell you how many iterations to do, because we could keep doing this forever. But I think what you would see is if we always kept 4 significant figures, the next iteration is probably still going to give me 0.6417. Because do you see how it changed quite a bit, going from 1 to 0.6572, and it changed a little bit on the next iteration, going to 0.6418, but then we only changed a very, very tiny amount on the third iteration here. And so our changes are getting smaller because we're getting closer to the true answer. So the answer to our question, what's the solution of cosine of x equals square root of x? It's x equals 0.6417 to 4 significant figures of accuracy. If you wanted more figures of accuracy, you'd have to do a few more iterations, but that's the idea.
So eventually, like, if you kept taking it, you would just keep getting 0.417 as the answer? Like, if you did more rows, it would just...
In fact, we can do that really quick. Excel makes this super, super duper easy and fast. If I want to open up Microsoft Excel, and we're going to make the same columns. And then that ratio of f of x of k minus f, they're divided by f prime of x of k. Let's see what we get, because k is equal to 1, 2, 3, 4, 5, 6. My initial iterate we decided was 1. And to take the function there, I take cosine of that number minus the square root of that number. And then to get the derivative, I take negative sine of that number minus 0.5 times that number raised to the power negative 0.5. And then I take the ratio of that number divided by that number. And then Newton's method says take the previous iterate minus this ratio for the Newton's method formula. And in Excel, the great thing is you don't have to type in the formula every time. You can just grab the cells and then on the bottom right corner, click the corner and then drag it down. And it'll just fill in the table for you. And so, you want to know with lots of digits of accuracy what the heck this number is. Hold on, let me fix the formatting. You can get as many digits of accuracy as you want if we just keep doing the iteration enough. But you can tell even after just 4 iterations of Newton's method, it converges really fast to the same number. Like I'm looking at these and I don't see a single digit differently after that. But does that answer your question? The more iterations we do, then you reach a fixed point where every iteration just keeps giving you the same number back. And that's how you know it's the solution. Good question. You can tell how much each iterate is different from the previous one by looking at this column, right? Because this is what you're subtracting to get the next iterate. And so if this is a small number in the last column, then you know Newton's method is not moving around your sequence very much anymore. And so as soon as this number gets small enough for you to be happy with your level of precision, you say, yeah, okay, that's small enough. I'm fine with whatever my 4th iterate is. Okay. Very good. So I want to show you one more thing. I want to show you the picture of what this looks like, because I think it's so important to always use Desmos all the time. I need to open in a new tab. And I'm going to save that for later. And I want a new function, f of x equals cosine of x minus square root. So in red, that function is cosine of x minus the square root of x. And our starting iterate is going to be the number 1. And what's happening if I start with x equals 1 is I find the value of my function and I find the slope of that function. I create a tangent line approximation. do you see how this black line here is the tangent line to the red curve? It's really a good approximation here. It's not so great of an approximation over here on the left side, right? There's a little bit of a gap. So I find my next iterate by finding the place where the tangent line is 0, where it intersects the x-axis. And then at that point, my new iterate, I evaluate my function and I get the value of that red curve. And then I find the slope of that function by taking its derivative and everything. And then I solve for the 0 of that tangent line. And now the tangent line is a really good approximation of the red curve. And so you find where that tangent line has a 0, which is right there. It's not exactly the same as the 0 of your function. So once again, you repeat the process. Take the value of your function, take its slope, find the tangent line approximation, find where that tangent line has a 0. And this time, it's a really, 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 really good approximation of the 0 of the function. Maybe there's a little bit of a difference, but not much. And so that's kind of the picture of what's actually happening with Newton's method. It gets a little bit more interesting if you take different initial iterates, right? Like, this is a spoiler a little bit for what I was going to teach later in the lecture. But if I started with the initial iterate 4.2, this doesn't really work so well. Because if you look, I'm taking a tangent line, the 0 of the tangent line's over here, then I take another tangent line and the 0 of the tangent line's over here, and I take another tangent line and the 0 of the tangent line's over here. And it's bouncing back and forth, trying to find a 0 of my function, but the function doesn't have a 0 over here. And so sometimes Newton's method can fail to converge. And so this is a big topic of study, and like I said, our numerical analysis class in MNU is like figuring out what is the interval of starting iterates that actually will converge to the 0 of this function, and how will we know if it's about to fail and it's not going to converge? That's a topic I discussed last week with my numerical analysis class, in fact. So there's more that you can study here. There's a lot of depth to this topic. Okay, we'll do another one. Use Newton's method to find a 0 of this function, x cubed minus 2x plus 2, starting at the initial iterate x is equal to 3. And so we're going to do this by hand, because on a test, you'll need to be able to do it by hand. And so let's give you some more examples of what to do. By hand, I'm going to make a k column, and then an x sub k column for all of my iterates. And then I've got to take the function evaluated at x sub k, and then the derivative of that function at x sub k, and then the ratio of the function divided by its derivative. And then to get my next iterate, I'm going to need to use the Newton's method formula, which says my next iterate is equal to the previous iterate minus that ratio that we calculate. And to start, k is equal to 0. And my initial iterate that I'm supposed to use is negative 3. Now, let's work in parallel here. You can get out your calculator and try to fill out the table. I'll get out my calculator and try to fill out this table. And we'll see what we get for 3 iterations. I made a mistake. Made a dumb calculator error.
Yeah. That's right.
Yeah, if you're trying to check your answers against mine, I made a little mistake. I knew I made a mistake because I noticed that my iterates were getting farther apart and not closer together. And so I thought, well, this could be diverging and failing, right? Because Newton's method can fail. Or maybe I just made a dumb calculator mistake. So I started going back and checking my work, and that's when I caught that I made that mistake. So unfortunately, that's the reality of working with calculators, is that it is easy to punch in the wrong number or miss a minus sign or forget to use parentheses or something, and it will really mess you up. Oh, I'm so dumb. I did the same mistake. Okay, I said 3 iterations was enough, so if you get to 3 iterations, tell me if you end up with the same answer as me.
So when you say 3 iterations, you mean not including the first iteration?
Yeah, what I mean is, like, I had to use Newton's method 3 times.
Okay.
Because the first time I used Newton's method, I get this x1. And the second time that I use Newton's method formula, I get x is 2. And the third time I use the Newton's method formula, I got x3. That's the third iterate. Yeah, what was really throwing me off about this dumb calculator is I really thought that if I typed in something like -5 squared, that it would give me a positive 25. No, it would give me a negative 25. And so I made that mistake like twice. And each time I made that mistake, I had to go back and find the mistake and erase the numbers that I had calculated using the wrong number. And that's why it took me so long. But yeah. Another good reason to use Excel when you can as an engineer, because Excel will help you avoid those things and quickly apply your formulas. And if you make a mistake, it's easier to fix, and you don't have to personally go back and calculate everything. Excel is a great tool. Speaking of, I might as well do this one in Excel too. It's x cubed minus 2x plus 2. And so this is what it looks like to do x cubed minus 2 times x plus 2. And then the derivative was 3 times x squared minus 2. And my starting iterate was -3, I think. And so what we would eventually converge to is -1.769. And after 3 iterations, we were at -1.777, which is pretty close. That's what we were supposed to get. Okay, any questions about this one? No? So again, to get our visual intuition here, let's use that function, x cubed minus 2x plus 2. And that function is here in red, and we want to dial into the starting iterate where we have -3. Our starting iterate. Yep, -3. And so, you kind of got to zoom out, but you start at -3, you find the value of the function. It was way down here at -19. You find the slope of the function so you can make a tangent line approximation. The black line is a tangent line, so it's close to my red curve over here, and then it starts to get farther away from the red curve so that the 0 of that tangent line is not exactly the 0 of the red curve, but then you repeat the process, find the value of your curve, find the tangent line slope, find the 0 of the tangent line, and that is 1, 2 iterations. On the third iteration, we find the value of the function, we find the slope, we zoom in to find the 0 of the tangent line. That is what we got for our third iteration at like -1.777. And if we were going to continue to iterate, then you go out here, find the curve, find the tangent line, find the 0 of the tangent line, and we're getting closer and closer and closer to the 0 of the function. As close as you want. Arbitrarily close. You want to get closer, you just do more iterations. So, all right. I think we've got time to finish these lecture notes. We might have to work a little bit quickly, but we can do that. Making a table. We're supposed to start at the iterate x equals 0, and it's the same function. So let's talk through the function together and find what is f of 0. That would be 0 cubed minus 2 times 0 plus 2. So that's 2. The derivative of this function was 3x squared minus 2. And so 3 times 0 squared minus 2 is -2. 2 divided by negative 2 is negative 1, and 0 minus negative 1 is 0 plus 1, which is 1, right? Now, we got to take this function evaluated at 1, which is going to be 1 cubed minus 2 times 1 plus 2. So that's 1 minus 2 plus 2, which is 1. Now we take the derivative evaluated at 1, which is 3 times 1 squared minus 2, which is 3 minus 2, which is 1. And 1 divided by 1 is 1. So what is my second iterate? 0. Because 1 minus 1 is 0. But if I start with a 0 in this column, what are the next 3 columns going to be? This has to be 2. This has to be negative 2. This has to be negative 1. And then my next iterate has to be 0 minus negative 1, which is 1. And if that's a 1, then f of 1 is 1, and f prime of 1 is 1, and this ratio is 1. 1 minus 1 is 0. So then my fourth iterate is 0. Do you see what's happening? Every odd number iterate is going to be 1, and every even number iterate is going to be 0. It's just going to bounce back and forth between 0, 1, 0, 1, 0, 1 forever. And this is what happens occasionally, sometimes. Oops, I need this to be 0. And the reason is clear. At 0, this is my tangent line approximation, and it leads me straight to the 1. And at 1, this is my tangent line approximation, and it leads me straight to the 0. It just bounces back and forth forever. So that's one way Newton's method can fail. And then let's find a 0 of the function arctangent. We're supposed to start at 2 different initial iterates, so we're going to work this problem 2 different times. If I ask you to start at 2 iterates, like on the homework, it says to start at 2 iterates, what I mean is first work the problem with x0 equals 2, and then after you're done, throw that paper away, get out a fresh sheet of paper, and work it again with this initial iterate, okay? Now, let's do this in Excel so that we can save a little bit of time. My function was arctangent, and I'm going to start where x is equal to 2. And this is my arctangent function. I think it's just atan in Excel. Yeah, it's atan. And the derivative of arctangent is 1 divided by x squared plus 1. But you got to use parentheses for that denominator. So 1 divided by x squared plus 1, and that's the problem, right? These numbers are getting really big, really fast. It doesn't look like it's converging into anything. It just looks like the numbers are getting massive. They're diverging away to infinity. So it's clearly failing to converge when I try to find a 0 of the arctangent function with Newton's method. And, you know, maybe you know this, but arctangent does have a 0. This is my arctangent function. And so this is the picture of what's happening if I start at x is equal to 2. I go up, find my function, find its slope, take the tangent line approximation, it shoots me over here to get the 0, and then I use that to find a new tangent line approximation. And do you see how the red curve is just getting more and more shallow as it goes off to the left and to the right, like it's getting flat, flat, flat? So the flatter the slope of the function, the flatter the slope of the tangent line, and the farther the tangent line has to go before it finds its 0. And this just continues to repeat, so it's spiraling outward in this picture. But there is a point, at least, where we can cross over, and if I choose an initial iterate that's close enough to the 0, then it will converge. Right? This is the same function, but if I just start with the initial iterate x equals 1.2, then I do get a situation where it does get closer and closer and closer to the 0 of the function. And so the deal with Newton's method is that Newton's method can always find a 0 of your function if you start close enough to where the 0 is.